they can be written in a variety of different ways, but usually if you have something of the form where f of x and y of x is equal to a constant, um, if this happens, then you know that f is a solution to the differential equation. In particular, if we take the total derivative of this thing and compare, we're going to have a function of m of x and y times dx plus n of x and y dy. That's going to equal 0. So m and n are functions of x and y. Um, and what that tells us then, or when does this occur? Well, if the partial of n of m with respect to y is equal to the partial of n with respect to x, then the solution of f of x, y of x is equal to a constant. So these are really nice to solve. If you have a differential equation in this form, then check the exactness criteria. This is what is required for it to be an exact equation. And then that allows us then to, once we find this capital function, this capital F function, it'll allow us then to solve the differential equation um, with a little bit of work, but not much. It's actually pretty straightforward. So let's try an example and explain kind of like what we mean by that. So this is 6x y minus y cubed dx plus, over here we have 4y plus 3x squared minus 3xy squared dy equals 0. Okay, so that's our differential equation. We want to check to see if it's exact. And so to do that, let's look. Here is my m. Here is my n. And so if I take the partial of m with respect to y, I'm going to hold the x and the constant. So I get 6x here. The y's cancel out. And then minus, reducing that 3 y squared. Okay, so this is the partial of m with respect to y. And now the partial of n with respect to x. The 4y is a constant, so I can ignore that. This is 3, bringing that down, so you can give me a 6x minus x's derivative of x is 1 here, so this is minus 3y squared. And comparing these two, you find that they are indeed exactly the same. So taking either one, it doesn't matter. We're going to try to find that function, that capital F there. And so we want to integrate one of them. And so if we pick on m, since it's the first one here, we know that df dx is equal to m of x and y. So we're going to integrate this m with respect to x, which means we're going to integrate this function here with respect to x and see if that gives us our function, a candidate that we can test then with respect to n to find out if it is indeed the same. So let's go ahead and do that. So f of xy, we assume is going to be of the form integrating m, we have 6xy minus y cubed. Notice I'm integrating m, not the partial of m. Okay, so I'm integrating m dy, sorry, dx for the m part. So integrating that gives me 3x squared y minus xy cubed plus an arbitrary function of y. So the arbitrary function of y comes from the fact that if I differentiate f with respect to x, this is a constant and it disappears. And this, well, the derivative of this is this, which was our m that we saw earlier. Okay. Now we also have an n of x and y that we can utilize to compare. So this is our f. Then if I take a derivative of f, so df dy, if I take a derivative of y with respect to this, I get 3x squared minus 2xy squared plus g prime of y. It's a y cubed. Sorry, this should be a 3. I knew something didn't look right. This is a y cubed, so the derivative of this with respect to y should be a 3 x y cubed, y squared. Okay, that looks good. All right, which is equal to g prime. Okay, and now let's set this partial derivative equal to our n and compare. Okay, so this is supposed to be equal to our n of xy, and that is 4y plus 3x squared minus 3xy squared. Okay, so if we compare the 3x squared, that's going to cancel, and a negative 3xy squared, that's going to cancel. And so it looks like g prime of y is equal to 4y. Mhm. Um, so if we integrate both sides here with respect to y, you get g of y. It looks like is what 2y squared plus a constant. And so we can rewrite f then, going back up here to our original. We can go back up here to f. So we have f of f now, since we know that it's a solution, and we know that f is a solution to it's equal to some constant, and we know that f we have f here. This is f, but we also know now what g of y is. Okay, so plugging everything back in and rewriting f, we have then that f of x y is equal to 3x squared y minus x y cubed plus what was g of y? G of y is what we just found, plus 2y squared plus, that's a plus, another arbitrary constant. Okay, and so this then is the value of the function. And if we set that equal to 0 and move the constant over, that would be the constant, and that would solve the differential equation. So this is the f that helps solve this differential equation. All right, I hope that was helpful, and I'll see you in the next video.